It's exciting to be here, partly because this is a beautiful place, and it's so good to meet so many lovely people. But also because this gives me an opportunity to retake an old project of mine that I had shelved for no good reason at all, many years ago. No good reason at all. I had a lot of projects and I had to get on with them. And now it's a really good opportunity to be able to say more about it and to continue to develop it. It's essentially a historical project looking back onto the works of Henry Margenau. So I'm going to tell you a little bit, I'm going to tell you quite a bit about who he was, what he was up to, and why it's worth us thinking about what he was doing again. Right. So first of all, I'll tell you something about the larger project that this project is part of. My larger project that has been going in the philosophy of quantum mechanics for a while. So you can see what is it that interests me about this. And then I'll focus on Henry Margenau, who he was, and his philosophical sources, who was behind the development of his main idea, the idea of latencies. And then I'll do something that has not been done, which is to look into the contextual setup of and development of his work, and in particular, I'll be looking at his competitors and his interlocutors at the time that he was developing these ideas. And these three main people will appear, whom I'm sure you'll know, and they play a role of different kinds. Carnap, Popper, and Heisenberg in this story. Won't be able to say much about them, particularly I won't be able to say much about Heisenberg, but I'm very glad to know that tomorrow we have a talk partly on Heisenberg, partly on Bohm. And then what I'll do in this second and final part of the talk is that I will actually do a little bit of critical analysis of this historical material. So I think there are parts of Margenau's latency ideas that are really worth recovering. We should think about them again. But I also think there are some problems with this approach, and we can do a little bit better than we did at the time, partly because we know so much more about the sorts of properties and approaches that he was employing. So I'll try to convince you that Margenau couldn't actually solve the measurement problem, which I think is the central problem in the philosophy of quantum mechanics. But if we just improve a little bit on these ideas, we possibly could solve it. So he was basically thinking along the right lines, although not completely in full detail, thinking right about some of these topics. Okay, so the larger project, and it's just a bunch of publications of mine to show you that I've been concerned with dispositional accounts of quantum mechanics for a long time now, and you can find lots of details of things that I've done over the years, defending dispositional interpretations of quantum mechanics in its many different forms. Many years ago, I started doing this historical project looking at the historical development of dispositional accounts in a paper that appeared in Studies. And at that time, I even gave a few talks which involved Margenau, at least in part. And then, as I mentioned, I shelved this project, not because there was anything wrong with it, because I have lots of good feedback. But I had other things that I had to get on with and work on, particularly with the philosophy of models and representation and so on. So it's really nice to be able to sort of retake this. And looking at the literature, I'm amazed that nobody picked on this and published the stuff already. So it's all still incredibly fresh. So who is Margenau? You probably don't know who he is because we don't talk a lot about him these days. But at the time that he was writing, he was one of the most well-known, if not perhaps the best known, philosopher of physics. In fact, he was the founder of many of the main institutions and setups that we nowadays associate with the foundations on the philosophy of physics, as you will find out soon. He was the president of the Philosophy of Science Association and was involved in its foundation. And he was one of the founders of the official journal of the association, Philosophy of Science. He did many other things that really got the philosophy and foundations of physics up and going. So only for his institutional contributions, he should be remembered and celebrated. But as I will try to argue today, he also had some major contributions to the philosophical foundations of quantum mechanics. He has a long life. He was German, born in Bielefeld, from a very humble working class background. He was very poor when he was a child. Trained as a school teacher in Latin, classics, German history, literature. He was clearly talented and endowed and managed to go to good schools. Finally, poverty was too hard, too much, and the whole family emigrated to the US in 1921. Initially, he was a farmer working in Nebraska. Eventually, he made it into the University of Nebraska for an undergraduate degree in experimental physics. And that led to a scholarship at Yale in 1929. He arrived in Yale in 1929 to write a PhD thesis on experimental aspects of the Zeeman effect on cerium. This was supervised by a very well-known X-ray spectroscopist at the time, Margenau. He never left Yale. Let's say he got there in 1929. He stayed there forever, except for visits abroad and so on. And one of those visits was to Sommerfeld's Munich Institute. Came back from that, was appointed instructor and assistant professor in theoretical physics at Yale, and eventually he made it quite big with Jane Higgins, professor of physics and natural philosophy. This is sort of important to this story that I want to tell. And he became emeritus and he was at Yale all his life. The one thing about Margenau is that he was instructed in philosophy. You already saw that he had elementary school instruction in classics and Latin and so on. And throughout his career, he constantly published both philosophy and physics papers from the start. And the philosophy papers were published in very serious, high-ranking philosophical journals. And the physics papers were published in high-ranking peer-reviewed, very difficult to publish in physics journals. So he basically was good at both. He was not an amateur either. And he took both very seriously from the work. I mentioned that he was one of the founders of the Journal of the Philosophy of Science Association and published a number of papers in the first few issues. The first few issues of Philosophy of Science, I recommend you go and take a look, are really amazing. The first 6 years, any name that you can think of is published in there. All those people published there. Margenau published a number of papers there. And he was clearly part of this early crowd that got the philosophy of science going in the USA. In 1936, he publishes this textbook, Foundations of Physics, which became the textbook in the Foundations of Physics for a whole generation of American physicists. Nowadays, we don't check it out, but it's actually an interesting book. Lots of pretty good ideas there. Then 1939-40, very important year for him. He spent it at the Institute of Advanced Studies in Princeton, where he met and became lifelong friends with Wigner and Wheeler. And he was instrumental in developing the problem of measurement with Wigner in the 60s. So those papers are normally associated with Wigner. Many of them are developing friendly cooperation and collaboration with Henry Margenau. Another very important event in his life is the arrival of Cassirer at Yale. Cassirer arrives in 1941, very eminent exile, an émigré from the Marburg Neokantian school, very important also to the logical empiricists and the logical positivists, who are all at that time moving over to the United States. He was one of the last ones to make the move. He was at Yale for a couple of years, and he moved to Columbia, where he was appointed a professor, and he eventually died there in 1945. Cassirer and Margenau were in constant collaboration. Margenau sat in Cassirer's classes at Yale, and they co-taught modules together as well. Part of Margenau's attempt to bring physics and philosophy together. In 1943, he published this book, which again is not very well known nowadays, but it was very impactful at the time, The Mathematics of Physics and Chemistry. This was a key introductory textbook for physics and chemistry undergraduates, no philosophy in this book, for a wonderful textbook. In 1950, he published what is his magnum opus in philosophy of science, The Nature of Physical Reality. And here he defends, clearly influenced by Cassirer. Cassirer had major impact on Margenau. He defends a neo-Kantian approach to philosophy of science. And from 1954 onwards, he develops this latency interpretation of quantum mechanics. The earliest paper is 1954, and there are a number of later papers. And he has a whole set of students working on this latency interpretation through the 50s and 60s. I mentioned that he was the president of the Philosophy Science Association. His collaboration with Wigner on the measurement problem. And one thing that I haven't mentioned is he was one of the two co-founders of the Journal Foundations of Physics, which we all know and love. So he also set that one up. So pretty much we wouldn't be here together in the way that we are, talking about what we're talking, had it not been for Henry Margenau. I think his contributions to the institutional setup of the philosophy of physics are really critical. I mentioned the influence of Cassirer, and Cassirer is a figure that looms really large in everything that Margenau writes from the 1940s onwards. So I want to do a brief summary of all of Margenau's philosophical theses, which many of them are inherited from Cassirer and then further developed by him. Now note that this is not necessarily an endorsement. I mentioned before that although I think many of Margenau's theories are very much worth discussing again, I don't agree with all of them. Ditto for Cassirer. I'm not really an Kantian. These two people clearly are. And so here's a list of the main theses that Margenau inherited from Cassirer. From substance and function, he took the critical theory of knowledge, this idea that our sensory representations must be embedded into an ideal framework of mathematical relations or laws for them to have an empirical object. And this is very much the neo-Kantian's critique of copy theories of knowledge, or purely empiricist accounts. From the philosophy of symbolic forms, Cassirer's maybe major work, Margenau took the genetic or genealogical conception of knowledge, and he took this to involve ever-evolving synthetic a priori frameworks with empirical content, which, to my mind, sound very much like what Michael Friedman has been doing in the last 20 years or so. In fact, Friedman mentions Cassirer a lot, but he doesn't mention Margenau. That's something that's missing. For the neo-Kantians, the synthetic a priori is taken to be a regulative ideal framework, as opposed to any kind of constitutive principle of knowledge, unlike the original maybe Kantians or the pre-Marburg school Kantians. And again, Margenau is very much following Cassirer there. And from Cassirer's main philosophy of physics treatise, which is determinism and indeterminism in modern physics, Margenau took a bunch of ideas. First, this idea that causality is a framework principle necessary for the possibility of any empirical knowledge of the world, which is shared by all Kantians, and which basically means that for Margenau, causation is a well-defined and a legitimate concept, if treated appropriately. He also derived from Cassirer the rejection of positivistic strictures or constraints on metaphysical principles, such as for instance, causality. So neither of these two thinkers are positivists. In fact, they're very consciously working against logical positivism. A derivative principal acceptance contra-positivism of metaphysical entities and properties, even though they may be unobservable as part of the mathematical frameworks used to account for the empirical world. So he was not a positivist, he was not a verificationist, he was not an operationalist in any meaningful sense in accounting for the acquisition or the definition of scientific knowledge. And that is partly what led him to latencies, because latencies are supposed to be unobservable properties of quantum systems in a way that we will go on to define. We'll talk about that in a minute. And that partly is made legitimate by this neo-Kantian background. In the 60s, in the 50s and 60s, he had a plethora of students who developed his latency approach into a full account of quantum measurement. These are just some of the PhD students that he trained, and some of the many contributions to the measurement problem. So there was definitely a school, a Margenau school, of people working, following pretty much his ideas and applying them particularly to theoretical and foundational issues, mainly to do with the measurement problem. Much discussed at the time, often I think unfairly ignored today. And I mentioned that I wanted to mention the competitors and the interlocutors. Mainly these three figures loom large in much of what Margenau writes. There's first of all Carnap, who Margenau knew and they interacted often. There is Heisenberg, and I apologize for the Heisenberg picture, it's trademarked, but it's very difficult to find any pictures of Heisenberg from the 1950s, and I wanted to identify pictures of these people roughly at the time they were having the exchanges with Margenau. So Carnap in the 40s and Heisenberg in the 50s and Popper in the 60s. Heisenberg sort of disappears. And there's no, you can't find images of Heisenberg in after the war. So this is the best that I could find. So these three people are very important for him in different ways. Carnap, there is a lot of respect between them going on, but they clearly differ. And they both refer to each other, but they disagree. And they're very aware of their disagreement. Heisenberg and Margenau were very close, and in fact, they defended very similar views. Who took them? I suspect it was Heisenberg who took them from Margenau. I can't find any smoking gun evidence in the papers that I've looked at that say so. But they're very close. They have very similar views. Popper, this is a difficult one. Clearly, they knew each other. They were both pretty dominant figures at the time. Popper went on to develop a propensity interpretation of quantum mechanics. I find it really hard to believe that Popper didn't know Margenau's earlier latency interpretation, but he never mentions Margenau in any of his papers. It's nowhere to be found in Popper's writing. So something is going on there, but I can't quite tell. Well, I can imagine, but I can't tell what it is. So Carnap had been dealing with these positional notions for quite a while before Margenau came up with latencies. The stability meaning is one of his great papers, where he develops a strictly imprecise theory of these positional terms like solubility. His aim is to reduce the possession of these positional terms to the truth of observational statements regarding the empirical manifestations of these terms. So basically, you want to understand something like solubility in terms of what happens to soluble objects when you place them in liquids. And he does this by means of so-called reduction sentences, which were much discussed in the 40s and 50s. Basically, something is soluble if and only if a number of conditionals that state what happens when that object is tested are true about that object. And that kind of logical reduction of the term allows, says Carnap, for a purely imprecise account of these modally charged terms. Now, Margenau clearly knew Carnap's theory very well, but he rejected it because he was basically a positivist and rejected any positivist or strict empiricist constraints on science or metaphysics. And Carnap knew of Margenau's work and similarly thought it was far too metaphysical and not rooted enough on empirical observations. And so basically, they were very aware of their very distinct philosophies of science. But as I mentioned before, they were very respectful of each other. They both had a common fatherly figure, right? Like this, Cassirer was the link between them. With Popper, the story is much harder to tell, as I mentioned. Popper came up with this propensity interpretation of probability, and this is important. It's not a propensity interpretation of quantum mechanics, it's a propensity interpretation of the calculus of probability. This is very distinct from what Margenau does. Popper claims to be independently developing his view. That doesn't cite Margenau anywhere, but Miller and Redhead report that Popper was aware of Margenau's school. It's very hard to think that he would have missed him. He missed the founder of these things going on. But one can imagine that Popper wouldn't have liked the Margenau approach because he didn't have enjoyed the neo-Kantian stuff. As a critical rationalist, Popper would have rejected the view that propensities may be part of the neo-Kantian constitutive probability framework. Instead, he identified propensities with probabilities and considered them conjectural entities, open to empirical verification and refutation in the Popperian falsificationist spirit. Nowadays, Popper's interpretation of quantum mechanics is widely regarded as a failure. If you want to know more about this, you can ask me in the question time, because I can give you a number of pretty decisive arguments against that. But it is important that it is a propensity interpretation of probability. That's not what Margenau is doing. Margenau would have rejected the idea that propensities were merely the business of interpreting probabilities. Margenau was in the business of interpreting quantum properties, not quantum probabilities. And this is a critical difference between the two, which makes Margenau's approach viable in a way that Popper's approach isn't. And finally, there's Heisenberg, about whom I'm going to say very little, but in 1955 and 1958, and I've noticed this paper, right? I've noticed that paper. Heisenberg came up with all these ideas about Aristotelian potentialities playing a role in the interpretation of quantum mechanics. This is about the same time that Margenau was developing this. Margenau arguably a bit earlier. And so therefore that leads me to suspect that if there is direct influence here, it would have gone from Margenau to Heisenberg. But as I mentioned at the beginning, I have no proof of this. At any rate, they thought very similarly about these things, and they have very similar views. But Heisenberg didn't develop this into a full interpretation of quantum mechanics in a way that Margenau and his school did. But clearly, there's a lot of affinity in this too. So let me now move on to the critical part, where I try to explain what latents are supposed to do and why I think they fail and how they can be improved upon. So you all know this. In quantum mechanics, systems are represented by states, which in turn are represented as vectors in Hilbert space. Properties are operators acting on the Hilbert space. Then systems can be in eigenstates when they happen to be in the eigenstate of the permission operator that represents the observable. And there's this fundamental semantic link, the eigenstate eigenvalue link, that tells you when a quantum system takes on a value of a given property. And what it says is that it takes a value of a given property if and only if the system is in the eigenstate of the operator representing this property. And I think this is all very well known to people. And the eigenstate eigenvalue link is a critical part of the orthodox interpretation, but it appears in many of our different interpretations of quantum mechanics. Okay, so here is a paradigmatic question for an interpretation of quantum mechanics. How do we interpret a system that is in a superposed state, not in an eigenstate of the permission operator that represents the property of interest, but in a superposition. And this paradigmatic question has a generic dispositional answer that Margenau was very good at articulating, namely, and Heisenberg was basically saying the same thing, namely that what it means for a system to be in a superposition is that the system has not a categorical property, but a dispositional property, a disposition, a tendency, a propensity, or a capacity to exhibit a particular value of that property if a measurement is carried out on the property of the system represented by a model. So if it's in the eigenstate, it has the categorical property, but if it's in a superposed state, then it only can have a dispositional property. And every dispositional account of quantum mechanics says something like this in response to that question. There are other ways of answering the question that are not dispositional, but those are not dispositional interpretations of quantum mechanics. Margenau and Heisenberg were both defending versions of dispositional accounts, and they both had an answer to this question very much along these lines. But it's more specific than this, and it's when we get to the specific details that things get a little complicated. Here's what Margenau says, a lengthy quote, which I cannot really summarize. So I'm going to read it, and I invite you to read it along with me, because there's some really good things in this quote, and then there are a couple of troubling things in this quote. There's a proposed shift of attention. The contrast, or at any rate, the difference is now between possessed and latent observables. This is his term, introduced expressly by him in 1954. Possessed are those like mass and charge of an electron whose values are intrinsic, do not vary except in a continuous manner, as for example the mass does with change in velocity. The others are quantized, have eigenvalues, are subject to the uncertainty principle, manifest themselves as clearly present only upon measurement. And I believe that they're not always there. They're not always there. This is a sentence that I've had to live with for years now. I wish that Margenau hadn't written this. I believe that they're not always there, that they take on values when an act of measurement, a perception forces them out of indiscriminacy or latency. If this notion seems grotesque, this is a part of the quote that I really like. If this notion seems grotesque, let it be remembered that other sciences, indeed common sense, employ it widely. Happiness, equanimity, are observable quantities of man, of some men, of some people, but they are latent qualities which need not be present at all times. You don't need to be handing out money all the time to be thought to be a generous person. It's just an act that when tested properly, you respond in the proper manner. Dispositional properties are not constantly and permanently being manifested. They just manifest themselves when the conditions are. So there are latent qualities which need not be present at all times, and they too can spring into being or be destroyed by an act of inquiry, a psychological notion. So I guess suggesting quantum properties are just like this. They're latent in just this way, but they don't need to be manifesting themselves all the time. I think there's a lot of really good stuff going on in this quote, but there's one particular thing that's troubling, and that's the sentence, the phrase where it says they're not always there. Why is this troubling? Let me try to explain what's troubling about this. This is the question that any interpretation must answer. The basic template of any dispositional interpretation of quantum mechanics must say something along the lines of this. So what it means for a system to be in a superposition is that the system possesses a latent property, as Margenau would say. And this is a disposition, a capacity, tendency, or propensity, like equanimity, happiness, generosity, to manifest or display certain eigenvalues upon the measurement of that property. And what's characteristic about quantum mechanics is that the dispositions that it deals with are probabilistic dispositions, unlike the case of solubility, equanimity, or velocity, because the properties manifest themselves with a certain probability given by, as you know, the Bond rule, by finding out the square modulus of the amplitude of the wave function. So for any property we want to measure, if it's a latent observable, when we carry out the measurement, it's going to give us a result with a certain probability. And that's the act of instantiation, exemplification, or actualization of what's an underlying latent property. That's the basic idea. Now, Margenau says these observables are not always there. That is, they're not there when they're not being measured. And here I think he makes a mistake. Because what he's basically saying is that there's only a latent observable if and only if there is a property that is being manifested as a physical quantity that gives a value. Otherwise, it's not there. The latent property is not there. So if the electron is not manifesting its position, then it does not have a latent property, a latent position, a latent property of position. If there is no physical quantity, then there's no latent observable. That seems to me to be what he's saying. So he seems to be defending something, implicitly, something like what I would call Margenau's E-link, that a quantum system possesses a property if it takes on a value of that property corresponding to the Hermitian operator, and that entails that it must be in the eigenstate of the operator that represents the property. But if he's committed to this, then he's going to have the same problem solving the measurement problem as the ordinary standard eigenstate eigenvalue. And if you don't believe me, then we run very quickly through a basic model of quantum measurement. We let the initial object in a superposed state of the property of interest interact with an apparatus in the ready state. The measurement interaction is a dynamical evolution of the composite, which must be in accordance with the Schrödinger equation in the composite. That throws the whole composite into a superposed state, which is normally referred to as the environmental infection of the superposition. And so the final state of the composite is given by that expression. But if you apply the eigenvalue length to that expression, we find out that the system has no value. It doesn't take a value in that state of the property of interest. That's what the ordinary eigenstate eigenvalue length gives you, and that's the origin of the measurement problem. This is in essence, but this is my version of the measurement problem. There's also Margenau's version of the measurement problem. So the idea that there's an inconsistency between these three different assumptions, they run into some kind of inconsistency. And now, if Margenau implicitly adopts what I've called Margenau's E-link, then I claim he can either solve this problem. Because on Margenau's version of the eigenstate eigenvalue link, the quantum system again possesses the property if and only if it is in the eigenstate of the operator representing that property. So in that final state of the composite, it is not true. You cannot say that the system has a value, and therefore it follows that the system does not possess the property. On his idea that latent observables are not there when they're not being manifested. So I think this must have been a slip when he says the observable is not there when it's not manifested. That must have been, that's a mistake. It's a slip in his account. Because if that's true, then you're identifying observables essentially with properties, associating properties with physical quantities, and therefore committing yourself to Margenau's eigenvalue link. And I've reconstructed that paragraph in this way. But that won't solve the measurement problem. And to really be coherent, what a dispositionalist has to do is to abandon this eigenvalue link and embrace instead something like what I've called the dispositional eigenvalue link, which is the idea that the quantum system possesses a dispositional property or latent observable, even when it doesn't take a value of that observable, latent observable or dispositional property. So it's not necessary for a system to be said to possess a property that it is in the eigenstate of the Hermitian operator that represents that property, if the property is one of these latent dispositional property. So Margenau should never have said the latent observable is not there when it's not being manifesting. You should have said the observable is there, but it's not manifesting itself. It's not allowing you to say that it takes a value, right? Not until you make a measurement, but it's nonetheless there. Just as the object is soluble, even when it doesn't manifest the solubility. Had he said this, I would have been much happier. Well, I wouldn't have to be doing all this work to put this right. Having said this, I think he would have had the beginning of a really good and interesting solution to the measurement problem. Because then he would have been able to say that quantum systems may possess properties, even if those properties do not always take values in those systems. Just as any dispositional property can be possessed without being simplified or actualized. And so therefore latent observables are latent precisely in the sense that they are there latently, even if they take no values. And if he had said that, he could have said electrons have positions, even if though they do not have, there is no particular position that they have. Their position is latent. It's just ready to be revealed on an active measurement. This can be made sense of nowadays in ways that Margenau could not have anticipated by, amongst other things, appealing to the distinction between determinable and determinate in analytical metaphysics. I think that's a good way of trying to understand this distinction. And I guess if Margenau had known all these analytical metaphysical distinctions, he would have developed it in this way. That's my guess. We can only guess. But certainly, I think there is something like a promising avenue to solve the measurement problem, at least in a conceptual manner, by following this kind of sophisticated rendition of Margenau's latent observables idea. So here are my conclusions. I think Margenau is insightful. I mean, he's wonderfully insightful in everything he writes. He writes a lot of things, he writes lots of different topics. But I think his main fundamental contribution, which is the latency idea, is insightful, even though I think it was not fully developed. And the fundamental idea here is that quantum properties are dispositional. That's what it means to say of an observable, but it's a latent observable. I think a proper recognition of this fact can solve conceptual puzzles in quantum mechanics. But this forces you to embrace fully and explicitly this basic dispositional template, and to say that a propensity latency is required as a proper reading of the Born-Body statistical interpretation of the state vector. And you may have a neo-Kantian understanding of propensities or latencies as providing a regulative framework for empirical knowledge. Margenau certainly did have it. I think this is a kind of optional commitment. I hope it is, because I'm not committed to it. But finally, I also want to add, this idea of latencies are a striking example of something that Margenau really cared for throughout his life, namely his belief in the importance of philosophy within the practice of physics, and philosophical reflection as part and parcel of what is to do good physics and come up with solutions to physical problems. So whether it fully works or not, it sort of exemplifies beautifully this lifelong commitment of Margenau to employ philosophy and philosophical tools to solve physical issues and problems. And that's all that I have to say.
Wow. Such years. Okay. And then 96. So yeah.
Oh, by the way, I should say, I put lots of pictures of people which so that's talk of the day. You must be tired.
Oh, actually, yeah.
Take this one. So again, just a short question that does Margenau consider this, that when you, if you like, actualize one latency, like when you measure position, then that will influence what you should expect about momentum, in the sense that these two are kind of related to each other or dependent on each other, and if so, how could the other not exist?
How would you?
Well, you, in the sense that how would the other not be there if there's
Yeah, for me,
if position momentum depend on each other?
Yes, so he claims the uncertainty relations are a fundamental law of latent observables. So you have the latent observable for position, the latent observable for momentum, and if you actualize position, then you cannot actualize momentum at the same time. It must remain latent. And if you actualize momentum, then position becomes inherently latent, it cannot be actualized. So he has a reinterpretation of Heisenberg's uncertainty principle as a principle that applies to latent observables, not to fundamental properties.
Right.
So, and what that means is that nothing mysteriously unlocked happens because you're not changing the categorical property of the position of the particle by measuring momentum, right? And there's a similar solution to the ER, like paradoxes, by the way.
But just a quick follow-up, but you do change your expectations that it, for example, if you do measure, define your position, then your expectations about momentum will change because then that will become very undefined.
Yes, because the rate
Right.
changes and therefore the expectation for momentum will change.
Right.
Yes.
May I raise two questions? The first is, you said that
dispositional properties can go without propensity interpretation probability.
Yes.
So
You mean the point against Popper?
No, I just want to ask, what was Margenau interpretation of, say, the Bohr rule for dispositional properties? If you said that the propensity interpretation of probability does not work, in any case, Margenau did not subscribe to any kind of this kind of probability interpretation. So what kind of probability interpretation did he have?
He talks in different places about frequencies, but he's not committed to a frequency interpretation of probability either. He's not an empiricist, so he doesn't move to a frequency interpretation of probability. I don't think he has an interpretation of probability. But so much the better for him. So I actually think no interpretation of probability works. Not different than this. So the difference with Popper is that Margenau thinks that quantum properties are probabilistic dispositions. Popper thinks that probability in general must be interpreted as propensity. Well, at least objective probability. If probability is objective, it must have a propensity interpretation. And so Popper gave this blanket propensity interpretation to the calculus of probabilities, the Kolmogorov calculus of probabilities. If they represent anything objective, they must be propensities. And that's what leads Popper into trouble. Margenau has no commitment of that kind. He has no commitment to the idea that all objective probabilities must be interpreted as propensities. Probability is a kind of undefined term for him. It cannot be fully, it's a fine format. It cannot be fully philosophically interpreted. And this is critical because his interpretation of quantum mechanics does not rely or depend on a propensity interpretation of probability, unlike Popper's.
So second point was if Margenau has an indefinite position on the collapse of the wave function. The role of the interpretation, because I read that he is credited for introducing for the first time the expression projection process. Maybe I read that somewhere. Anyway, whether he had any definite position.
Well, this is so pre-GOW, and there's no clear sense that collapse is an interpretation, one more interpretation among all the others. But I think it's implicit in everything that he says. I mean, in fact, I would say anybody who defends a disposition on account of quantum mechanics is in some ways committed to a sort of collapse interpretation, namely the actualization of potentialities. So if you are a dispositionalist, you think quantum observables represent a bunch of latent qualities or dispositional qualities, and the actualization of one of them upon measurement collapses that observable onto the actual eigenstate of the system. So there is something like a collapse going on. But I don't, at least in the 1950s papers and in the books, Margenau doesn't call this collapse. So this must have come later. By the way, Heisenberg, I don't know the other people who have looked into it, but I can't make sense of anything that Heisenberg says in physics and philosophy if it's not as a collapse interpretation of some sort. So I think he was also commenting.
I was going to ask a question, but now I want to make a comment. When you say collapse of the wave function, it sort of suggests there's a process, there's some mechanics missing. As opposed to, okay, if there's an actualization, why would one think about a process there?
Yeah.
That suggests a sort of intuitive, mentalistic, classical, maybe even somehow continuous
That's a good
thing.
question.
So let's suspect things, maybe one reason why he loses that phrase. So what I wanted to ask you is, did you find in reading a Margenau, because I've read his things, but not systematically, any mention as you find in Heisenberg, who may or may not have been influenced by, did any discussion of Aristotle? Because it's critical in a certain way.
There are discussions. I mean, he has lengthy philosophical introductions and he discusses Aristotle and
His father was a classical philosopher. Heisenberg's father. Right, exactly. Exactly. Yeah. So
but Margenau too. Margenau too knew Aristotle very well, and his nature of physical reality has lengthy introductory chapters in Aristotle, but it doesn't play a role, as far as I can tell, in the latency interpretation.
But so, I mean, latency, we find this in Aristotle.
Yeah.
It's fine, like you've got a blind marble, it has a latency for a statue of a man.
Yeah.
So how do you protect it from what you see as the error?
So the fact that he was knowledgeable and provenly knowledgeable about Aristotelian philosophy, employs the concept of latency and doesn't give any nod to Aristotle suggests to me that he's just not committed to Aristotelian first metaphysics of any kind. He's a neo-Kantian. He doesn't think you can talk about the nature of objects and their properties independently of the whole mathematical framework that we employ in developing the quantum theory. So I think this is a critical difference between Heisenberg and Margenau. Heisenberg is not a neo-Kantian. I mean, Heisenberg is not a philosopher, first off.
That's
right.
That's
Well, he's not a professional philosopher. He didn't publish many philosophical articles. He published a book with the title Physics and Philosophy. Margenau is thoroughly trained philosophically, and I think he's just not an Aristotelian. He's too much of a neo-Kantian to think that there are first nature.
You were supposed to see that.
Yeah, that's six. No. Here's what I didn't see your hands. No, I did with my hand, but please, sorry. We can say stuff like this. Give the word. No. I wanted to say something. I saw your hand. So it doesn't matter, but I'll be very quick. Why do you think that there is a beginning of a solution to the measurement problem? As far as I can see, it's just a restatement of the problem. Because, I mean, for my mind, also had a sort of a solution, right? Because investments process one. But we are not considering it as being a solution, it's just the problem. How come the measurement, if thought about as physical interactions, why is it the case that the measurements collapse, even if it has a collapse, which it doesn't? Why is it that measurements tend to exhibit the relating to.
Because they exemplify the testing conditions for the appropriate dispositions. That is, when measurements are appropriately carried out, not every measurement will, but when measurements are appropriately carried out, they instantiate in the real world the conditions that abstractly test those dispositions or actualize them. That will be his answer. That will be any dispositionist answer. Now, that's not going to satisfy you, Mayor, because you are a skeptic of this persistent. So therefore, the starting point is just different. Margenau will never convince you, but he convinces me.
Okay. First, just a quick comment regarding Federico's question. I'll check tonight, but I think I've got a memory that in 1935 or 36, Margenau explicitly rejects the collapse postulate. That he's saying that he wants to remove the projection postulate from quantum mechanics. But I'll check. I was wondering whether you were being uncharitable to Margenau. Can you put up sort of the main quote with the basically they're not there. And, so now I believe that they're not always there, that they take on values when an act of measurement and perception forces them out of indiscriminacy or latency. If he says that, he must mean that they are latent before the measurement.
Good. I mean, this is the bit that I like. The forced amount of indiscriminacy or latency bit, I like it. I just wish he had not written this.
Well,
What is it?
Principle of charity. You must mean something else. I mean, not always there. In quotation marks. What does that mean? That we don't know. But measurement forces them out of latency. That's completely clear. So you must mean something else when they're not always there.
And I'm trying to say what he means. It's trying to say they're not always manifest.
Well, that's the right way of reading it, I agree. But why didn't he say that? I mean, I believe that they're not always manifested, would have been very nice. But he doesn't say that's what it's not always there. I mean, this has a corollary that some of the work that then gets developed by his students, I think, falls into the not always there. So if you read Knight and Park's papers, they will continue to say things like the particle has no position, it doesn't have a value of position, and so on. And I think that's because they're taking this reading of the not always there. They have some consequences in the posterior literature. But no, I totally agree. I just take this out, and this quote is just everything you need to know.
You should edit the corrected paper. So we have one last question.
Yes, thank you. Well, so you don't think that quantum latencies are irreducible? They are not irreducible according to your method. Because if they are irreducible, it's a way of explaining what happens when a latent property becomes manifest. For instance, the collapse theory or the geothermal account. You want to have an account about what happens when a latent property becomes manifest. You're not happy just to say it becomes manifest. You want to know why and how. That was my problem. So you don't want to say these latent properties are not reducible to category. That was my question.
I do want to say that.
But then you don't.
I mean, do you mean reducible in the, for instance, in Carnot's sense?
No, not in that sense.
Okay.
No, I meant that you can have some sort of a constructive story about mechanism. Like demonstrating collapse. Yeah.
Yes,
I'm not sure it's objection.
but yes, no, I don't think Margenau is opposed to the idea that there may be some ulterior story to be told about latencies. In fact, when he reinterprets the uncertainty relations as a relation between latencies, he's ascribing structure to latencies. So we may say he's telling you something about the structure or the nature of it. In that respect, I don't think he was a skeptic, and neither am I. I mean, I think he may occasionally find very precise mechanisms that operate behind dispositions. I mean, solubility is right. But we now have a pretty good theory of solubility in crystal registers. But sometimes you get that story, and that's great, but sometimes you don't, and you still want to accept the dispositional account because it does some work for you. And in the case of quantum mechanics, we don't have that mechanistic story, but nonetheless, the dispositional functions do work for you. I mean, they don't do work for me because it's model scatter.
Twice now, I'm doing the talk.
Right.
No, wait.
But what I wanted to say in terms of the debate with Carnap thought dispositional properties were analytically reducible.
No.
And I certainly don't think, and I don't think that.
Thank you so much.
Yeah.